So what we're going to do today is we're going to look some more at the redox chemistry. Yesterday we looked at the sort of the basic ideas about how you can split up an overall redox reaction into pieces. You have the oxidation and you have the reduction, where the oxidation is the part of the reaction where something loses electrons to make something else, and the reduction is the part of the reaction where something else gains electrons to make something else. And we saw about how you can balance those and you can put them back together, and we can use oxidation numbers for working out how to do that. And then right at the end we saw about this business about balancing for total charges on each side. What we want to do today is to go on a little bit more. Yesterday was very qualitative, right? You mix a thing with a thing and this happens. But as we've seen already in lots of cases, when we do science, we want to be able to put numbers on things. So today we want to start talking about how we can put numbers on and quantify these redox reactions. And to start, I want to play another little video, which again is one that we should be able to do in here, only we can't because the university would be very excited if we did this. So, if I just turn that back down a bit and we play this, we'll see how this looks. I haven't seen this before, this could be really bad, but... Oh, wonderful. Copper pennies into nitric acid. NO2 without the thing. So that bubbling, there's a tube coming out of that flask and into the water. So the bubbles is the gas being produced by the reaction. Oh, well, that probably makes the point. No, there's more. That'll probably do. We don't need to know that it's hamsters doing the chemistry. So, this is the reaction that I thought we were going to do in the labs, but we're not, because it's one we used to do and we don't anymore, where you take copper and you put it in nitric acid and you get these huge brown fumes pouring out of it. Now those brown fumes are our old friend NO2 that we talked about heaps when we were doing equilibria last week. So that brown gas is NO2, and the copper the copper metal, and the coins in this case, turns into a bluey-green solution of copper 2+ ions. Right? So, what I want to do then is to start today's lecture by looking at this reaction. So copper metal reacts with concentrated nitric acid. It has to be concentrated too. If you just have dilute nitric acid, even though it's still a strong acid, the reaction doesn't work the same. So that's interesting. Copper metal reacts with concentrated nitric acid to produce a brown gas, which is NO2, and a blue-green solution of copper 2+ ions. And so using the sorts of ideas that we developed yesterday, we could look at this and say, well, what are the half equations going to be? What's being oxidized? What's being reduced? And so the straightforward one's going to be the copper. Obviously you start with a piece of copper metal, so that's copper atoms in the metal, and that turns into copper 2+ ions. And so we could write an equation like this. Copper solid goes to copper 2+ plus 2 electrons. Okay, and in this case you kind of, well, the assumption is you know it's copper 2+ because if you could see up close in that flask you'd see that bluey green colour, which is very characteristic of copper 2+. But I wouldn't expect you to know that off by heart. Right? Because there's this thing at school, copper 2+ is always blue. Well, it's not. It can be a whole bunch of colours. It's just copper sulfate's blue, and that's about all you ever play with at school. Yeah. So copper goes to copper 2 plus 2 electrons, and so that's going to be a oxidation or reduction? This is an oxidation, yeah? Because the copper's losing electrons to make copper 2 plus. So this is an oxidation. And so the reduction must involve the nitric acid. And so we could start this equation by writing this. HNO3, aqueous, goes to NO2 gas. Now this equation is a bit of a tricky one. It's the sort of, if I was mean, I would say, right, go and balance that now. But what you would rapidly find is that you can't just balance it as it stands. If you use the rules that we used yesterday, you would say, well, I've got a hydrogen, a nitrogen, and 3 oxygens on the left-hand side, but I've only got 2 oxygens on the right-hand side, so that means I need to add a water to make up the difference in the oxygens. But then you'll find that you can't balance the hydrogens. It doesn't work. What you have to do is you have to remember that nitric acid is a strong acid, and so when we write HNO3 aqueous, what that really means is H plus and NO3 minus, okay? Or in the acid-base chemistry, H3O plus and NO3 minus, but for this redox stuff, just H plus, right? And if we split that up like that, then the balancing becomes a bit more straightforward. So maybe I'll give you a couple of minutes or so to have a go at balancing that one out with the electrons, just using the sorts of ideas we talked about yesterday. So we're going to do this first of all by balancing for the oxygens. Right, we've got 3 oxygens on the left-hand side, only 2 on the right-hand side. So we add a water. So now we've got 3 oxygens on each side, so we're balanced for oxygens. And then we can go back and balance for hydrogens by putting a 2 in front of the H plus. Right? And you can see what the problem would be if you just wrote HNO3. Then you would, if you put a 2 in front of the H, you'd have to put a 2 in front of the HNO3. Then you've suddenly got more oxygens, so you have to add more water to the other side, and then you just go round and round in circles. Right. Okay, so that's going to be the overall, well, that's going to be the balanced for atoms one. 2H plus NO3 minus goes to NO2 and H2O. And then we need to put some electrons in there to finish it off. It's a reduction. Remember, the copper one was an oxidation because the copper loses electrons. So this must be a reduction, so the electrons go on the left-hand side. And to work out how many, we can work out the total charges. The total charge on the left-hand side is going to be +1. And the total charge on the right-hand side is 0. And so we can finally balance that up by just adding 1 electron to the left-hand side. And then we can combine those two equations together, the copper one, the oxidation, and this, which is the reduction. So have a go at that. That's the next slide, but have a go at that. So there's our oxidation. There's the reduction one that we've just worked out. So when we add those together, we recognize the first one's got 2 electrons, the second one's only got 1 electron. So we have to double everything in the second equation, like that. Add them together, cancel out the electrons, and get the overall equation. Right. So we're getting the hang of these then? That's kind of a curly one because of this business about the HNO3, but you have to write it as H plus and NO3 minus. But again, all the sorts of ideas we talked about yesterday are just what we're doing here, right? So that kind of leads us into then where I want to talk about today. We can maybe get this later if you haven't quite got all that down. That if we take a piece of copper metal and we put it in concentrated nitric acid, we get this crazy reaction that we saw in the little movie, right? You get all these brown gas just pouring out of it, and it gets really hot. You can't tell that from the video, but it gets really hot. And the metal dissolves and you get this green solution. And the copper is oxidized, and so we would call the nitric acid solution the oxidant in this case, right? The copper loses electrons, so it must be the nitric acid which is causing it to lose electrons. Otherwise, it would just sit there quite happily as copper metal. And so the nitric acid solution is the thing which we call the oxidant. But interestingly enough, if you then took some copper pennies or a piece of copper metal and you put it in concentrated hydrochloric acid, nothing happens. It will just sit there and look at you indefinitely. As soon as you put it in nitric acid, it immediately starts reacting very violently and vigorously, but in hydrochloric acid, nothing happens. They're both strong acids. Why should there be a difference? Well, the difference is because HCl is not able to pull the electrons off the copper. It is not a good enough oxidant. So we have two acids. One of them is able to pull electrons off a copper and turn it into copper 2+. The other one is not able to, and so the copper doesn't react. Okay? So that must mean that if we can say that the nitric acid is a better oxidant than the hydrochloric acid. And so that kind of implies that there must be some range of oxidant strength that you can get depending on what molecule you are. Right? Some are good, some are not so good. And so immediately we go, as fledgling scientists, well, if there's a range, we must be able to put numbers on them and rank them and stuff. And so that's what we're going to be talking about from now on today, is how we go about putting numbers on these things to tell how good an oxidant they are. It just occurred to me there's another example like this, which of course, if you think about it, you know. If you take a piece of sodium metal and you throw it in water, what happens? It reacts vigorously, right? And that reaction will be the sodium turning into sodium plus cations. So the sodium is being oxidized by the water. But if you take a piece of copper and throw it in water, what happens? Nothing, right? And this is why if you're rich, you use copper for your roofs and for your spouting and for your, oftentimes still for all the plumbing in your house, right? It's all copper pipes. Because by and large, the copper doesn't react with water, even though sodium reacts very easily. And so again, we can say that even though now we're reacting with water in both cases, the copper is much less keen to give away its electrons to something else than the sodium is. So different abilities of being a reductant. Okay. We can quantify the oxidizing ability of an oxidant by quoting something called the reduction potential. And the reduction potential is given the symbol E, and if it's something called the standard reduction potential, and we'll come to what that means in a bit, then it's E with a wee circle on it. So that's like delta H standard with the delta H with the wee circle. The standard kind of refers to the same things as it did for delta H, but kind of not to be fair. Now, just out of interest, how many of you who've seen this sort of stuff at school were taught reduction potential, and how many were taught electrode potential? Was anyone taught electrode potential? You were? Just one. How many saw reduction potential? Okay, cool. Apparently there's a big swing in the chemical community internationally away from reduction potential and towards electrode potential. The textbook that you guys are going to use for 191 says reduction potential. And so I'm going to keep using reduction potential here, even though I apparently am bucking the new way that these things are supposed to be taught. So the reduction potential tells you about how much something wants to be reduced. And remember, being reduced means gaining electrons. Leo goes Gur. So this number tells you about how much something wants to get electrons from something else and so be reduced. Yeah? You can look up these numbers in books. We're going to look a bit later about where the numbers come from. But for the reactions that we're talking about at the moment, you can go and look up in your SI chemical data book the values for the reduction potentials, and you find that for this nitric acid one that we've just been talking about, the value for E standard is plus 0.80 volts. The unit of the reduction potential is volts. And again, we're going to see why that is after morning tea. So the number's plus 0.8 for the nitric acid one. For the copper one, oh no, here's the one, sorry, for HCl. For HCl, here's the equation that you have, and see it's a slightly different equation now. When the nitric acid is reduced, it's reduced to NO2 in water. For hydrochloric acid, the reduction is just H plus gaining electrons and turning into H2 gas. Right? And you may well have seen that reaction somewhere, because that's the thing when you put like zinc in hydrochloric acid and then you do the pop test thing, yeah, to check that you're making hydrogen. This would be the reaction that happens there. The H plus ions are reduced to H2 gas. And the number for that is 0.00 volts. Now, it turns out that equation has a number of 0 by definition. I mean, again, we're going to talk about this more later. But that 0 number doesn't mean it doesn't want to be reduced. It just means it doesn't want to be reduced as much as the H plus NO3 reaction does. Right? So there's something inherently about this mixture of things which means it wants to gain an electron and turn into these more than these want to gain electrons and turn into these. Right? If we look up our copper number, oh no, we still don't have that. The value for E standard is more positive for the nitric acid, and so we say that it is the better oxidant. Right? And we saw that before, because we just said if you compare the reactivity with copper, nitric acid reacts, hydrochloric acid doesn't, so nitric acid seems to be a better oxidant. Now we have some numbers that we've looked up which back that up. Because the number for the reduction potential for the nitric acid is plus 0.8, and the number for the reduction potential for the HCl is just 0. The one for the nitric acid is a more positive number, so that means it's a better oxidant. It wants to get electrons more. Let's look in more detail at these E standard values. What we do is we quote them like this. We'll say, for example, for the one for silver, E standard for Ag plus / Ag equals plus 0.85 volts. Right? Again, we've gone and looked up that number in our book. This little part that we write after the E standard that refers to the reaction that's happening, we write these two things in a particular way. We write the oxidant first. So if the reaction, because remember this refers to a reduction reaction. A reduction potential refers to a reduction. So it'll be silver plus gaining an electron and turning into silver metal. That's the reaction that this number refers to. Yeah? So when we write these two things here, silver plus will be the oxidant. It is the thing which is reduced. And then, perhaps surprisingly, we write the silver and we say that the silver there is the reductant. Now what we're going to see is that these reactions can go either way. And the thing which my colleague and I who teach 191 are in the process of trying to work out is how much we're going to make a big deal about the fact that all these reactions are equilibria. Because it's traditionally not something that we've done. But I'm starting to wonder whether this will help. All of these little half equations we've been talking about so far, in theory, are all equilibrium reactions. And so they can go one way or they can go the other. The number refers to Ag plus going to Ag, right? Just the same as a KSP refers to the solid dissolving to give the ions, not the other way. Yeah? But it is conceivable that silver could turn into silver plus in some redox reaction. And if that was the case, then the silver would be the reductant. It would be the thing that enables the other thing to gain electrons because the silver itself is losing the electrons and turning into silver plus. Yeah? And so we call the silver plus the oxidant and we call the Ag metal the reductant, even though you wouldn't call it the reductant in the reaction of Ag plus going to Ag. Does that even remotely make sense? It's not a big deal if you don't get this yet. Right? The important thing is that the first thing is the oxidant. And when we write this number like this, the reduction potential refers to the reaction of Ag plus gaining an electron and turning into Ag. Right? Yes?